Welcome back to the second section of Chapter 1 of Calculus. This chapter, as we had discussed, talks about limits. In the first section, we looked at how we can find limits from the graphs of functions, and we also looked at the notation and some infinite limits. This section is going to be specifically how do we find limits without having to graph it, because graphing stuff and finding stuff by graphing is great for estimating, but it's time consuming and we don't always get the best, most exact answer. And so we're going to look to see some different ways we can find limits with the equations. The first method that we are going to use is substitution. This is by far the easiest, and it's always the first thing that you should do. Always try substitution first. And with substitution, it's just something like we have the limit as x goes to 4 of 3x squared minus 2x. We're just going to plug in 4 and see what happens. So when we plug in 4 here, we're going to have 3 times 4 squared minus 2 times 4. 4 squared is going to be 16. And then 2 times 4 is 8. 3 times 16 is 48 minus 8 equals 40. So that tells us that the limit as x goes to 4 of 3x squared minus 2x equals 40, because it actually came out to a number. This is what we were seeing a lot of times yesterday when there was nothing funny going on. When we can just plug it in and it comes out to a value like that, that's going to be the limit. This happens when the functions are continuous. I know that we haven't actually talked about continuity and continuous yet, but you've seen that in the past. I mean, there's no breaks in it, there's no gaps, there's no funny stuff. The limit should be whatever the function equals. And so what would happen if substitution doesn't work? We can use other stuff like factoring and canceling. So we're going to have limit as x goes to 3 of x minus 3 over x squared minus 9. Step 1, always substitute, because some of the stuff won't work if substituting doesn't turn out right. So when we substitute in 3 here, we get 3 minus 3 over 3 squared minus 9. 3 minus 3 is 0. 3 squared is 9, minus 9 is 0. So we have 0 over 0. Well, 0 divided by anything is 0, but anything divided by 0 is undefined. So what do we get here? We don't know. It could be all sorts of stuff. With limits, we can actually divide by 0. Kind of. We can take the limit as it goes because we can see what it's getting close to without it actually being that thing. But in essence, it allows us to basically divide by 0, which is fun. So since it's 0 over 0, we have to do something else. In this case, the something else is going to be factor and cancel. So we have our limit as x goes to 3. X minus 3 is already factored. We don't need to worry about that. That's just x minus 3. Then x squared minus 9, one of them is going to be x minus 3 because 3 made it equal 0. That means that 3 has to be a root of the denominator. So x minus 3, and the other one is x plus 3. This one, you should have been able to factor it pretty easily. I mean, it's just a difference of squares. But if we had bigger things, you know one of them is going to be x minus 3, and you can use that to help find whatever other factors you might have. Well, we have x minus 3 over x minus 3. That cancels, leaving us 1 over x plus 3. And so at this point, we're going to substitute again. We're going to plug it in. So our limit as x goes to 3 of 1 over x plus 3 is going to be 1 over 3 plus 3 is 6. So the limit equals 1 over 6. So in this case, 0 divided by 0 equals 1/6. But that's factoring and canceling. That would be our first step probably after substituting if we get 0 over 0. Now there is another option when we get 0 over 0, and that's going to be multiplied by the conjugate. It's basically actually the same thing as factor and cancel, but the way that the problem presents itself, factoring doesn't make much sense, and so we would do this instead. Example, we have the limit as x goes to 9 of x minus 9 over root x minus 3. First step, always plug in. So we're going to have 9 minus 9 over root 9 minus 3. 9 minus 9 is 0. Root 9 is 3 minus 3 is 0. So we have 0 over 0, so we have to do something else. Now factoring here, as I said, doesn't really make that much sense. Technically, x minus 9 could be factored to root x plus 3, root x minus 3, because x minus 9 is a difference of squares. It's just, it's a root x instead of an x. We don't usually think like this and see it like this. So multiplying by the conjugate would be the next logical step here for the do something else. So we have the limit as x approaches 9 of x minus 9 over root x minus 3. We're going to multiply by the conjugate of the one with the root x plus 3, root x plus 3. And now when we multiply, we're not going to multiply the numerator in this case, the one that doesn't have the root, like where it's not the conjugate. We're not going to multiply that because we're going to hope that this x minus 9 is going to cancel with an x minus 9 in the denominator. And that will generally happen that way. By multiplying it out, that's going to be a big headache. Then we'd have to factor. No, only multiply out the one where it's actually the conjugate. So we have limit as x goes to 9 of x minus 9 times root x plus 3 over root x times root x is x. Root x times 3 is 3 root x, and then minus 3 root x cancels out. That's the whole purpose of multiplying by a conjugate. And then negative 3 times 3 is minus 9. Sure enough, x minus 9's cancel, and we're left with just root x plus 3. Now plug it in again. So the limit as x goes to 9 here of root x plus 3 is going to be root 9 plus 3. The root 9 is 3 plus 3 is 6. So that's one example of multiplying by the conjugate, where again, I like this one because it really shows that multiplying by the conjugate and factoring and canceling is basically the same. However, sometimes factoring and canceling is going to be much more difficult, and you're not going to want to try that. For example, if we have something like this, x minus 2 over root x plus 7 minus 3, trying to factor that root in the bottom or the stuff in the top, that's not going to be somewhere where you're going to be very successful in that. So here's where multiplying by a conjugate is really important. It really comes in. But first, we always have to plug in 2, because we could get 0. We could get 1/3 here if we plugged in 2. We won't, but we could. So let's plug in 2. So we have 2 minus 2 over the square root of 2 plus 7 minus 3. 2 minus 2 is 0. 2 plus 7 is 9. Square root of 9 is 3 minus 3 is 0. So we have 0 over 0. So we can do something else. And that something else we're going to multiply by the conjugate. So let's get this written out. I'll give myself a little bit of room here. X goes to 2 of x minus 2 over root x plus 7 minus 3. Let's multiply by root x plus 7 plus 3, root x plus 7 plus 3. All right, now when we multiply again, we're not going to multiply the one that's not conjugates. X goes to 2. So the numerator will still stay as x minus 2 times root x plus 7 plus 3. The denominator, we're going to have root x plus 7 times root x plus 7. There's a 7 under there somewhere at some point, which is going to give us x plus 7. And then plus 3 times root x plus 7 minus 3 root x plus 7 goes away. Minus 9. X plus 7 minus 9 is x minus 2. Cancels, just like this one over here. It works out the same. It's just the roots and the numbers look a little bit bigger. And now we can substitute and we can plug in 2. So the limit as x goes to 2 of root x plus 7 plus 3 is going to be root 2 plus 7 plus 3. Root 2 plus 7 is 9. Square root of 9 is 3 plus 3 is again 6. So this one is one where multiplying by the conjugate is not really, I mean, that's the option. You don't have the, well, I could try and factor it option like the other one. So both of them are definitely very good skills to be able to have. And you wouldn't do both. It's not like method 1, substitution, and then we're going to try factoring, and then we're going to try conjugate. It's substitution, and then which one makes sense for the other two. There are more methods, but we're not there yet. These here. But we will look at some properties of limits. There's lots of properties. Most of the properties make sense, like they're what you would expect it to be anyway. So the limit of a constant is just the constant. If you have y equals 5, when x approaches 3, it's 5. When x approaches 7, it's 5. It's always 5. So it's just a constant. The limit of a linear function. Does a linear function have any like holes or gaps or anything that would keep it from being whatever it is? No, we could always find this by substitution. So if we have the limit as x goes to a of x, it's just going to equal a. It's going to equal whatever that number is. And this is the parent linear function, y equals x. We can change that to other linear functions with some of the next properties, but this is just the parent function of it. The sum of limits, if you have two limits, it's both going to the same value. You can add the two numbers together. So if you knew the limit as x went to 2 of f of x was 7, and the limit as x goes to 2 of g of x was 1, the limit as x goes to 2 of f of x plus g of x would just be 7 plus 1, which equals 8. So you can add the limits together. What makes this one really nice is you can split up polynomials into their individual terms, and it's the same thing. So like the limit as x goes to 3 of x plus 2 uses these two. We can split it up to the limit as x goes 3 of x plus limit as x goes 3 of 2. You plug it in, you're going to get 3 plus 2 is going to be 5. So that's where that really gets used a lot. And we don't really use it like explicitly. It just allows for a lot of stuff that we do to actually work out. In this section, you may be answering questions where I give you what the limit is, and then you just have to use some of these properties. But usually, it just kind of works in the background. The next one, limit of a function times the constant. You just multiply by the constant. So like the limit of 3x is going to be 3 times the limit of x. So you can multiply either inside the limit or outside the limit. It doesn't matter. And again, that works in the background to help split up like linear functions and polynomials and stuff like that. Couple more. Product of limits. If we're multiplying things, we can multiply the limits. So if we have, like, say, the limit of x times x, which is x squared, that's the limit of x times the limit of x. So that works out. And then quotient of limits is the same, with the exception that the denominator can't equal 0, because then you get weird stuff like what we were just looking at, where it could do a lot of different stuff. So pretty much with limits, you can do with them what you think you should be able to. It's multiplying, you can multiply them. It's dividing, you can divide them. They're adding, you can add them. And so, again, that shouldn't be hugely surprising there. And then limits and substitution. When can we just use substitution? It'd be nice if we had some things where we know that, hey, we can just use substitution here and find the limit. And there are some. There's a theorem, the limit of a polynomial theorem, which says that if it's a polynomial, then you can just substitute and the limit will equal that value, which, being that there's nothing weird happening, it's continuous. Again, we haven't talked about continuous, but you know what it is. Then the value will equal the limit. There's no holes, there's no breaks, there's nothing that's gonna make it anything but that. So any polynomials, you can find the limit by just using substitution. Other functions that you can find the limit by using substitution, the sine function, again, there's no breaks, nothing funny happening. Cosine, exponential, and logs, as long as it's in the domain. So a has to be greater than 0, because if a is less than 0, then it's not in the domain. Square roots, and cube roots. So again, notice all of these are continuous functions. And these, along with the polynomials, those are the functions we see more often than anything else. The fact that you can find the limit by just substituting is great. The thing where we end up with problems is when we have quotients, where we have the fractions where you end up with a 0 over 0 or something like that. That's where the work comes in, once we really get into it. And then the limit definition, last slide. Limit definition. I know we've defined the limit. It's what the function's going to, what we think it should be at a certain value, things like that. This is the official definition. It's called the epsilon delta form of the definition. It is not required that you know this, like have it memorized or anything like that. I like showing it because I think it's good to see what some of these definitions look like, seeing the notation, seeing the variables, and it's good to know, but you don't have to like really use this definition at all. And so what this definition says, the epsilon delta definition of a limit, for a function f defined in some open interval containing a, but not necessarily a itself, we say. So what is that? It means that the function has to exist in an interval. Like it has to be defined. So like the square roots, you can't do the negative domain for the square roots. That doesn't work. The function actually has to be there. It's an open interval. It doesn't have to be defined at the endpoints of this interval, and it doesn't have to be defined at the value that we're looking at. It needs to be defined everywhere around that value, though. So the same stuff we've been looking at with graphs yesterday, we're looking at where it's defined around. The limit is x goes to a of fx equals L if given any number, epsilon, which is greater than 0, there exists, that's what that symbol means, a delta greater than 0, such that the difference between x and a is less than delta guarantees. So if you're close enough to a, that means that you are within epsilon of your limit. If you are close enough to a, you are within a very small value of the limit that you're trying to show. You might not be able to get to the limit. It might be undefined at that point. But again, if you get close, you're going to be within a certain amount. And then there's actually an addendum to this where as you get closer, as delta gets, or as epsilon gets smaller, no, as delta gets smaller, epsilon will also get smaller. So as you get closer and closer to the x value, your y value will also get closer and closer and closer. Again, this is not something you need to memorize or anything like that. You should you should know it just as in a conceptual thing, but it doesn't change the definition of limit. It just kind of formalizes it a little bit. And so that is section 2. I hope you enjoyed it. I'll see you next time. Until then, keep working problems, keep asking questions, and as always, happy mathing.